The SR-71 Blackbird reached speeds exceeding Mach 3.2, 2,200 mph, making it the fastest air-breathing crewed aircraft ever built. This remarkable achievement was possible because of its revolutionary SR-71 Blackbird engine design, which could withstand temperatures hot enough to melt conventional aircraft materials. The SR-71 Blackbird engine represented a quantum leap in aerospace engineering. Its unique J-58 engines functioned as both traditional jet engines and ramjets, automatically transitioning between the two modes as the aircraft accelerated. The engine's sophisticated design managed extreme temperatures, handled complex airflow patterns, and used specialized fuel that doubled as a coolant. This video explores the extraordinary engineering behind the SR-71 Blackbird's propulsion system, from its innovative thermal management solutions to its advanced navigation capabilities. You will discover how Lockheed's engineers overcame seemingly impossible challenges to create an aircraft that still holds speed records decades after its retirement. Origins and development timeline. The genesis of the SR-71 Blackbird traces back to a critical moment in Cold War history. On May 1, 1960, when a Soviet surface-to-air missile successfully downed Gary Power's U-2 spy plane, it became clear that the United States needed a reconnaissance aircraft that could fly higher and faster than any existing platform. The U.S. military commanders urgently needed accurate intelligence about Soviet military deployments, particularly near the Iron Curtain. While Lockheed's U-2 had been effective, its relatively slow speed and vulnerability to Soviet interceptors prompted the search for a more advanced solution. The Central Intelligence Agency, CIA, and the U.S. Air Force recognized that rapidly developing surface-to-air missile systems posed an increasing threat to existing reconnaissance capabilities. Under the leadership of Clarence Kelly Johnson, Lockheed's Skunk Works division took on what seemed impossible, creating an aircraft that couldn't be shot down. The project began with a series of design proposals designated from a 1 through a 12, submitted to the CIA between April and August 1959. Each iteration aimed to meet an extraordinary set of design requirements: the ability to exceed 2,000 miles per hour, sustain high altitude, flight above 60,000 feet, and maintain a minimal radar cross-section to avoid detection. The development process was remarkably swift. After the CIA accepted the A-12 design in August 1959, they approved funding for 12 aircraft on January 30, 1960. The first A-12 achieved its maiden flight on April 26, 1962, and by July 1963, it had achieved a sustained speed of Mach 3.2 at 78,000 feet. The transition from A-12 to SR-71 represented a significant evolution in aircraft design. While the A-12 was primarily an overflight vehicle, the Air Force needed a more versatile platform. The SR-71's development began in December 1962, when Lockheed signed a contract to build 6 aircraft. The development of the SR-71 Blackbird introduced several key improvements over its predecessor, the A-12, transforming it into an even more capable reconnaissance aircraft. One of the most significant advancements was the addition of a second crew position, designated for the reconnaissance systems officer. This role was critical for managing the aircraft's advanced surveillance and navigation systems, allowing the pilot to focus on operating the aircraft at its extreme speeds and altitudes. Another notable enhancement was the increase in fuel capacity, which extended the aircraft's operational range. This improvement was essential for the SR-71's long-duration missions, enabling it to cover vast distances without the need for frequent refueling. The SR-71 also incorporated cutting-edge reconnaissance systems, far surpassing the capabilities of the A-12. These systems provided unprecedented intelligence-gathering capabilities, allowing the aircraft to capture high-resolution imagery and electronic data from immense distances, even while traveling at speeds exceeding Mach 3. The first SR-71 took to the skies on December 22, 1964, and entered service with the 4,200th, later 9th, Strategic Reconnaissance Wing at Beale Air Force Base in January 1966. Throughout its nearly 24-year career, the SR-71 maintained its status as the world's fastest and highest flying operational aircraft, setting an absolute speed record of 2,193.167 mph and an altitude record of 85,068.997 feet on July 28, 1976. Revolutionary propulsion system. At the heart of the SR-71 Blackbird's exceptional performance lay its Pratt & Whitney J58 engines, each capable of generating 34,000 pounds of thrust. The propulsion system's innovative design allowed the aircraft to sustain speeds above Mach 3 for extended periods, a feat unmatched by any other air-breathing aircraft. The J58 engine featured a sophisticated design with several key components: a 9-stage axial compressor with an 8.8:1 pressure ratio, an 8-can combustor system with a modulating afterburner, a 2-stage turbine driving the compressor, and a variable geometry exhaust nozzle system. The engine made extensive use of nickel superalloys, particularly Inconel and Waspalloy, enabling it to withstand temperatures from 800 degf at the inlet to 200 degf in the afterburner duct. The SR-71 Blackbird engine design incorporated a revolutionary inlet system with a translating spike that moved approximately 1.625 inches per 0.1 Mach number. This spike could travel a total of 26 inches to optimize airflow at different speeds. The inlet system managed incoming air through. At Mach 2.2, the inlet contributed 13% of the thrust, the engine produced 73%, and the ejector added 14%. At speeds exceeding Mach 3.0, the thrust distribution shifted significantly, with the inlet generating 54%, the engine providing 17.6%, and the ejector accounting for 28.4%. The SR-71 Blackbird engine type represented a groundbreaking hybrid design that functioned differently at various speeds. At Mach 2.2, the engine began transitioning from a conventional afterburning turbojet to a turbo ramjet configuration. This transformation occurred when 6 bypass tubes diverted approximately 20% of the compressor air directly to the afterburner. The engine's unique design created a distinctive SR-71 Blackbird engine shockwave pattern that was carefully managed through the inlet system. The Lockheed SR-71 Blackbird engine achieved an unprecedented inlet compression ratio of 40 attentions, with the inlet assembly providing 54% of the total thrust at Mach 3.2. The Digital Automatic Flight and Inlet Control System, DAFIX, precisely managed the engine's complex operations, significantly improving vehicle performance and range while virtually eliminating inlet unstart problems that had plagued earlier control systems. This sophisticated system continuously adjusted the spike position and bypass doors to maintain optimal airflow conditions throughout the flight envelope. Thermal management innovations. Managing extreme temperatures posed one of the greatest engineering challenges in the SR-71 Blackbird's development. During sustained high-speed flight, the aircraft's surface temperatures reached between 600 degf to 900 degf, demanding innovative solutions in materials, cooling systems, and structural design. Lockheed engineers designed the SR-71 Blackbird to withstand the extreme thermal stresses of sustained flight using heat-resistant materials and innovative thermal management systems. Titanium was chosen as the primary construction material, making up 85% of the aircraft's structure due to its exceptional strength-to-weight ratio, resistance to temperatures as high as 842 degf, and superior thermal stability under stress. The titanium alloy used in the SR-71 contained 13% vanadium, 11% chromium, and 3% aluminum. This specific composition created a thermally stable oxide layer that prevented oxygen penetration at elevated temperatures, preserving the aircraft's structural integrity even during the intense heat of Mach 3 flight. The SR-71 employed an advanced cooling system that utilized its JIPE-7 fuel as a heat sink to manage the enormous heat generated during operation. beginning at temperatures below 0 deg. After high altitude refueling at around 30,000 feet, the fuel absorbed heat from critical aircraft systems, progressively warming to 177 degc before reaching the engines, where it was heated further to 316 degc for combustion. To prevent vaporization of the fuel within the tanks, engineers pressurized the fuel system using nitrogen gas from a 260-liter liquid nitrogen dewar. This pressurization increased the fuel's boiling point by 33 degc, enabling the aircraft to maintain extended supersonic cruise capabilities without compromising safety or performance. Thermal expansion posed another significant challenge during flight, as the intense heat caused the aircraft's skin panels to expand over 4 inches from nose to tail. To accommodate this, Lockheed engineers implemented several innovative structural solutions. The SR-71 featured corrugated skin panels on its wings and fuselage, which allowed for expansion without causing warping. Ground-level panel fittings were intentionally loose, aligning properly only when the aircraft reached its operational temperatures. Additionally, sawtooth panel joints were incorporated to absorb thermal expansion, preserving the integrity of the airframe. The SR-71's iconic black paint also played a critical role in thermal management. Far from being merely aesthetic, the dark coating functioned as a black body, optimizing heat radiation and aiding in the cooling of the airframe during high-speed flight. This passive cooling complemented the aircraft's active thermal management systems, creating a comprehensive and highly effective approach to controlling the extreme heat generated by its extraordinary performance. Advanced navigation systems. Navigation at speeds exceeding 3 times the speed of sound demanded unprecedented precision and reliability. The SR-71's sophisticated navigation systems represented a quantum leap in aerospace technology, enabling precise positioning even in hostile airspace where traditional radio navigation was unreliable. At the core of the SR-71's unparalleled navigation capabilities was the NAS-14 V2 Astro-Inertial Navigation System, a groundbreaking technology that allowed the aircraft to maintain extraordinary positional accuracy. Even after covering distances equivalent to halfway around the globe, the system's margin of error was less than half a mile, an impressive feat for its time and a critical feature for missions requiring precise reconnaissance. The NS achieved this remarkable accuracy by integrating celestial navigation with advanced inertial guidance. It simultaneously tracked up to 6 stars from a catalogue of 52 pre-programmed celestial bodies using their fixed positions to determine the aircraft's precise location. A specialized quartz window located behind the reconnaissance systems officer (ROSO) cockpit allowed the system's sensors to maintain an unobstructed view of the stars, even at the extreme altitudes where the SR-71 operated. The system further enhanced its precision by combining stellar data with inputs from an inertial platform and highly accurate chronometer readings. This integration of celestial and inertial navigation ensured real-time updates to the aircraft's position, while continuous cross-checking of positional data allowed for corrections that minimized drift over long distances. The NAS-14 V2's reliability and accuracy were essential for the SR-71's missions, enabling it to navigate hostile airspace with confidence while maintaining the precise routes required for reconnaissance and intelligence-gathering operations. This advanced system was a key factor in the SR-71's ability to execute its missions with unmatched efficiency and success. The SR-71 required exceptional navigational precision, needing to maintain position within. The aircraft needed to maintain lateral accuracy within 1,885 feet, 575 meters, adhere to a flight path with a maximum deviation of 300 feet, 91 meters, flight duration up to 10 hours. The system's pre-flight preparation involved loading mission parameters via a specialized Mylar tape containing electronically programmed route information. During operations, the reconnaissance systems officer, ROSO, managed the navigation systems, while the pilot focused on aircraft handling and system monitoring. The ANS represented a significant advancement in automated navigation, functioning as a 1960s equivalent to modern GPS, but using celestial references instead of satellites. The system's sophistication extended to automatic sensor activation at predetermined control points, real-time position updates through forward-looking site references, integration with the autopilot for precise route following and backup systems, including a Singer Kierfort SNEN 2417 INS with 1 NEM per hour accuracy. In 1982, significant improvements came with the replacement of the original gyro flight reference system. The new system featured an inertially stabilized platform with 4 gimbals, enabling all-attitude operation through vertical and azimuth gyros combined with 3 sub-miniature pendulous linear accelerometers. The navigation system's reliability proved crucial during missions where the aircraft operated at the edge of space, with the Russo handling the complex navigation tasks while monitoring the aircraft's sophisticated sensor suite. This division of responsibilities between the pilot and Russo created an efficient workflow that maximized mission effectiveness while maintaining precise navigation control. Stealth technology integration. Stealth technology in the SR-71 represented one of the earliest attempts at radar-evading aircraft design. Through innovative engineering, Lockheed's team achieved a remarkable 90% reduction in radar cross-section, making the 100-foot-long aircraft appear smaller than a person on enemy radar screens. The SR-71's unique profile was the result of meticulous radar deflection engineering designed to minimize its radar cross-section. Several key design features played a pivotal role in achieving this stealth capability. Inward-angled vertical control surfaces, sharp-edged chines along the fuselage, and a blended wing-body configuration all contributed to the aircraft's ability to redirect incoming radar signals away from their source, making them far less detectable. Additionally, the specialized positioning of the engines further enhanced the aircraft's radar evasion capabilities. These design elements collectively reduced the radar cross-section of the SR-71 to approximately 110 square feet, a remarkable achievement given the aircraft's size. The material composition of the aircraft's surface was another important factor in its radar reduction strategy. Titanium alloy, which made up 93% of the SR-71 structure, was chosen not only for its exceptional strength-to-weight ratio, but also for its ability to deflect radar waves. However, working with titanium presented unique challenges. The material required specialized titanium tools for construction, as it was highly sensitive to conventional manufacturing processes. Additionally, welding the alloy demanded precise conditions to maintain its structural integrity. The SR-71's distinctive black exterior was coated with a specially formulated iron-based paint that served multiple functions. Primarily, the coating was designed to absorb radar waves, further reducing the aircraft's radar reflectivity. It also provided enhanced thermal protection, crucial for managing the extreme heat generated during high-speed flight. Additionally, the black paint contributed to the aircraft's overall stealth characteristics, working in tandem with the design and material choices to ensure that the SR-71 could operate undetected at unprecedented speeds and altitudes. The SR-71 Blackbird's electronic warfare suite was a highly advanced system designed to ensure the aircraft's survival in hostile environments. Central to this suite was its state-of-the-art deception jamming technology, which employed a cutting-edge range gate stealing technique. This method worked by manipulating radar signals to create false target returns, effectively deceiving enemy radar operators and systems. The system's capabilities were both innovative and highly effective. One of its key functions involved absorbing and memorizing incoming radar signals. By analyzing these signals, the suite could replicate them with precision, ensuring that its responses matched the characteristics of the original radar. Building on this capability, the system generated ghost returns that were deliberately stronger than the actual aircraft's radar signature. These false returns diverted attention away from the SR-71, misleading enemy radars into tracking phantom targets. The cumulative effect of these countermeasures was to disrupt and confuse enemy targeting systems. The aircraft's electronic countermeasures (ECM) system worked in conjunction with its physical stealth features to create a comprehensive defense against detection and interception. When combined with its high-altitude capability and exceptional speed, these systems made the SR-71 virtually invulnerable to enemy air defenses of the era. The integration of these stealth technologies created such an effective defense that by the time enemy radar operators detected the aircraft, it had already completed its mission and departed the contested airspace. This remarkable achievement in stealth technology laid the groundwork for future developments in low observable aircraft design. Operational capabilities. Throughout its operational history, the SR-71 Blackbird demonstrated unparalleled performance capabilities that redefined the boundaries of aviation. The aircraft's extraordinary achievements stemmed from the perfect integration of its advanced systems and revolutionary design. The SR-71's performance statistics remain unmatched in aviation history. On July 28, 1976, the aircraft set two remarkable world records that still stand today: an absolute speed record of 2,193.2 miles per hour and a sustained altitude record of 85,069 feet. The aircraft's capabilities extended beyond these official records, with the ability to survey 160,934 square kilometers of territory in just 1 hour. Beyond these official records, the aircraft demonstrated an incredible operational efficiency that further underscored its dominance. Its remarkable speed enabled it to complete record-breaking journeys, such as flying from New York to London in just 1 hour, 54 minutes, and 56.4 seconds, and traveling from Los Angeles to Washington, D.C., in a mere 1 hour, 4 minutes, and 20 seconds. These achievements were not just technical marvels, but also strategic game-changers, allowing the SR-71 to operate with near impunity in contested airspace. Its ability to outrun enemy threats and deliver critical intelligence in real time secured its place as one of the most iconic and effective aircraft in history. The SR-71's operational range and endurance were equally impressive. Missions frequently lasted more than 6 hours and covered distances exceeding 11,265 kilometers. To achieve such extended operations, the aircraft employed a specialized fleet of Keek 135Q tankers for aerial refueling. The aircraft's remarkable efficiency was demonstrated when Majors Thomas B. Estes and Dwayne C. Vick completed a mission covering 15,000 miles in 10 hours and 30 minutes, earning both the 1971 Mach Trophy and the 1972 Harmon Trophy. The SR-71 Blackbird was equipped with an array of sophisticated reconnaissance technologies that enabled it to gather high-quality intelligence in diverse and challenging scenarios. These included high-resolution cameras capable of capturing incredibly detailed imagery, electronic intelligence-gathering devices that intercepted and analyzed enemy communications, and advanced electronic countermeasure systems designed to disrupt hostile radar and communications. Additionally, the aircraft was outfitted with sophisticated radar jamming equipment that further enhanced its ability to operate undetected in hostile environments. The role of the Reconnaissance Systems Officer, ROSO, was crucial in managing these complex systems. While also handling navigation duties, the ROSO operated the aircraft's surveillance equipment, oversaw its defensive systems, and was responsible for providing precise coordinates in emergencies. This dual responsibility ensured that the SR-71 could execute its missions effectively, gathering valuable intelligence while remaining secure from enemy detection. The aircraft's extraordinary performance allowed it to gather intelligence on a wide range of targets. It conducted surveillance of enemy supply depots, monitored harbor installations, assessed industrial complexes, and documented prisoner of war camps. The SR-71's missions provided crucial intelligence during significant historical events, including the 1973 Yom Kippur War, the Israeli invasion of Lebanon, and pre- and post-strike imagery of the 1986 U.S. raid on Libya. In 1987, Kadena-based SR-71 crews conducted vital missions over the Persian Gulf, identifying Iranian Silkworm missile batteries that threatened commercial shipping and American escort vessels. The aircraft's operational success relied heavily on its unique propulsion system. The J-58 engines, designed to operate continuously in the afterburner, achieved optimal fuel efficiency during Mach's 3 cruise operations. This remarkable engineering achievement enabled the SR-71 to maintain sustained supersonic flight while conducting complex reconnaissance missions in hostile airspace with complete impunity. Maintenance and support. Maintaining the SR-71 Blackbird demanded extraordinary dedication and resources, with each aircraft requiring approximately 24 to 36 hours of maintenance for every hour of flight. The complexity of its systems and materials necessitated a level of technical expertise unprecedented in aviation maintenance. The SR-71's maintenance program operated like a space mission countdown, requiring precise coordination among multiple specialized teams. Each aircraft was assigned a dedicated maintenance crew who worked in rotating shifts to ensure continuous support. The maintenance team structure included the aircraft manager, lead crew chief, specialized systems technicians, pre-flight inspection teams, post-flight analysis specialists, and environmental systems specialists. The program maintained exceptionally high experience levels through a Code 42 system, allowing mechanics to remain with the program for extended periods, some spending their entire careers maintaining the SR-71. The SR-71's titanium construction required unique maintenance equipment and procedures. Standard steel tools could damage the aircraft structure, necessitating the development of specialized titanium tools. The maintenance process itself was highly structured and relied on multiple specialized systems tailored to the aircraft's demanding requirements. A pre-flight inspection, taking approximately 4 hours and requiring 4 mechanics, was conducted to verify the aircraft's readiness before each mission. Similarly, a basic post-flight inspection of the same duration and manpower followed each mission to identify any immediate wear or damage. More extensive checks, such as the hourly post-flight inspection, involved 24 to 36 hours of work by multiple teams to evaluate and address deeper maintenance needs. The most comprehensive procedure, the phase inspection, conducted every 400 flight hours, took between 6 to 9 weeks and required the efforts of a full maintenance crew. The aircraft required specialized start carts featuring modified Buick Wildcat engines generating 500 horsepower each to initiate engine start procedures. These carts were necessary because the J-58 engine's specialized oil became nearly solid at temperatures below 86 degrees Fahrenheit. The SR-71's unique design and operating characteristics presented unprecedented maintenance challenges. Each flight typically resulted in multiple maintenance issues, with Code 3, significant problems requiring immediate attention, being the norm rather than the exception. Key challenges included: the aircraft's thermal expansion characteristics required precise handling procedures. During flight, the airframe expanded by more than 4 inches from nose to tail, necessitating specialized structural maintenance techniques. The fuel system posed particular challenges, as the aircraft deliberately leaked fuel on the ground due to panels that would only seal properly at operational temperatures. Heat-related engine and electrical problems proved especially challenging to diagnose, as many issues only manifested at speeds above Mach 3 and disappeared below Mach 2.8. Maintenance crews often had to replace components based on educated guesses since these conditions couldn't be replicated during ground testing. The Digital Automatic Flight and Inlet Control System, DAFIX, required constant attention, with inlet maintenance being one of the most demanding aspects of keeping the aircraft operational. The sophisticated pressure suit systems also demanded rigorous maintenance protocols, with each suit component requiring detailed inspection and testing before and after every flight. Periodic depot level maintenance, PIM, occurred every 800 flight hours at Lockheed Skunk Works facility in Palmdale, California, involving a comprehensive 6-month inspection and overhaul process. This deep maintenance cycle ensured the aircraft's continued ability to operate safely at extreme speeds and altitudes. Legacy and impact. Decades after its retirement, the SR-71 Blackbird stands as a testament to aerospace innovation, pushing boundaries that modern aircraft still strive to reach. Its contributions to aviation technology continue to influence cutting-edge aerospace development and research. The SR-71's design principles and operational experiences directly shape today's hypersonic vehicle development. The Air Force actively applies lessons learned from the Blackbird's development in its current hypersonic research programs. The aircraft's unique shape, complexity, and logistics requirements serve as crucial reference points for engineers designing semi- and fully reusable hypersonic vehicles. The SR-71 Blackbird engine design particularly influences modern combined cycle engine development. Current aerospace engineers studying hypersonic propulsion systems frequently reference the J-58's innovative features when tackling similar challenges in contemporary designs. The success of the Lockheed SR-71 Blackbird engine in managing the complex transition between subsonic and supersonic flight continues to inform modern propulsion system development. The SR-71 Blackbird's achievements in aviation remain unparalleled, solidifying its status as one of the most remarkable aircraft ever built. Its records, established decades ago, continue to highlight its extraordinary capabilities. In 1976, the Blackbird set an absolute speed record of 2,193.2 miles per hour, making it the fastest air-breathing manned aircraft in history. During the same year, it achieved an altitude record of 85,069 feet, demonstrating its ability to operate in the thin upper reaches of the atmosphere. The Blackbird also set time to distance benchmarks, such as flying from New York to London in 1 hour, 54 minutes, and 56.4 seconds in 1974, and completing the Los Angeles to Washington, D.C. route in an astonishing 1 hour, 4 minutes, and 20 seconds in 1990. Beyond its official records, the SR-71 consistently showcased its operational excellence. One of its most notable missions spanned 15,000 miles over 10 hours and 30 minutes, earning the Mach trophy in 1971 and the Harmon Trophy in 1972 for exceptional aeronautical achievement. Despite operating in some of the most hostile environments, the aircraft maintained a flawless mission success rate, with no losses attributed to enemy action. Its ability to survey vast territories at speeds and altitudes beyond the reach of adversaries ensured its status as a virtually untouchable reconnaissance platform. The SR-71 Blackbird engine type's innovations continue to influence modern aerospace technology. Its construction pushed the boundaries of materials science, particularly in the development and use of titanium alloys capable of withstanding extreme temperatures and stresses. The aircraft's design also introduced advanced thermal management systems, essential for maintaining functionality during sustained high-speed flight. Its supersonic inlet design principles became a foundation for future engine technologies, enabling optimized performance across varying speeds. Additionally, the SR-71's sophisticated electronic countermeasure systems provided groundbreaking advancements in radar evasion and signal manipulation. The SR-71 Blackbird engine shockwave management techniques developed for the J-58 engines remain relevant in modern supersonic aircraft design. The understanding gained from managing complex airflow patterns and thermal challenges continues to inform current aerospace engineering practices. Modern unmanned aerial vehicles, UAVs, and reconnaissance satellites have assumed the SR-71's role, yet none combine its unique capabilities in a single platform. The proposed successor, the SR-72, currently under development by Lockheed Martin, aims to build upon the Blackbird's legacy while incorporating advanced composites and 3D printed components. The aircraft's influence extends beyond military applications. Its thermal management solutions find applications in modern commercial aviation, while its materials science breakthroughs contribute to various industrial applications. The SR-71 Blackbird engine diagram continues to serve as a reference point for aerospace engineers studying complex propulsion systems. The Air Force's current work on next-generation combined cycle engines draws heavily from the SR-71's experiences. These modern developments aim to power future hypersonic vehicles from runway to hypersonic speeds, addressing many of the same challenges that the Blackbird's engineers successfully overcame decades ago. The SR-71's legacy in aviation history is further cemented by its perfect operational record. Despite over 4,000 missiles being launched against it during its service life, not a single Blackbird was lost to enemy action. This remarkable achievement underscores the effectiveness of its integrated design philosophy, combining speed, altitude, and stealth capabilities in a way that remains unmatched. The SR-71 Blackbird stands as a masterpiece of aerospace engineering, pushing technological boundaries that remain impressive even by today's standards. Through groundbreaking innovations in propulsion, thermal management, and stealth technology, this remarkable aircraft achieved speeds exceeding Mach 3.2 while operating at the edge of space. The Blackbird's revolutionary J-58 engines demonstrated unprecedented capabilities in managing extreme temperatures and complex airflow patterns. Sophisticated navigation systems and radar evading features allowed it to complete countless missions without a single loss to enemy action. These achievements stem from extraordinary engineering solutions, including specialized titanium construction, innovative fuel systems, and advanced electronic countermeasures. Many of the SR-71's speed and altitude records remain unbroken decades after its retirement. The aircraft's influence continues through modern hypersonic research programs and propulsion system development. The SR-71 Blackbird proved that seemingly impossible engineering challenges could be overcome through innovation and determination. While modern reconnaissance platforms have assumed its role, none have matched its unique combination of speed, altitude, and technological sophistication. The aircraft's legacy lives on as engineers apply its lessons to develop the next generation of hypersonic vehicles, ensuring its place in aviation history as one of humanity's greatest aerospace achievements. Aviation enthusiasts fascinated by this extraordinary aircraft's capabilities and achievements can share their appreciation. What about you? Are you fascinated by the SR-71? If so, please leave a comment to let us know. Thank you for watching.